All righty. We're going to start off the night. Well, first off, let me welcome everybody that I don't know. I'm Linda, the current president, and I want to welcome everybody tonight. We have anybody who's joining us the first time or new members who haven't been to a meeting before? Oh, Conrad, put your hand down. Pete, tell us about yourself.
Good afternoon from Hawaii.
Hawaii.
Wow.
Yeah.
Oh my God.
How did you find out about us?
Oh, I'm just a multi-decade buddy of the speaker tonight.
Oh, okay.
I'm here to keep him honest and to give
Well,
him a
that's
hug.
good. We welcome everybody. So
What time
Not
is it in
picky.
Hawaii?
we'll let anybody
just
in.
coming up to 2 o'clock in the afternoon.
Oh, okay.
It's
Okay.
pretty cold here. It's down to about 82.
Well, welcome. We're glad you could join us tonight. Chris, who is Chris here?
Hi, everybody. This is Chris Harkins.
Chris.
Hi,
Oh,
Chris.
Hey, Chris.
how are you?
Old member.
Been a long time.
Yeah.
Yeah.
Chris.
Wow.
Pretty good.
A blast from the past.
Wow. Still in Bellingham or Blackstone?
Blackstone probably till next year.
Okay.
We're thinking of selling out now. We're in Jamestown most of the time.
Uh-huh.
There's nothing wrong with that. Good to hear from you, Chris.
Yeah,
Yeah,
nice
very
seeing you
good.
folks.
I see.
Good to
Why
not
don't you
see
show
you.
us? Hey, you got turn on your camera if you
I
got
don't
one.
have a camera on this laptop.
Okay.
Okay.
Old tech.
Well, we'll accept that.
That's all
Not that
right.
Wayne,
old, but it's not
you're here
functional,
with us
so.
for the first time too, right?
I am indeed.
Yeah, Wayne is a fairly new member, so.
I joined last year. We just moved to Rhode Island last year. And so one of the first things I did was, since I'm back in the hobby after N number of decades, I won't fill in the N. I thought I would join up and meet some people and, join the community and have some fun.
Welcome.
So thank you.
Welcome. A lot of familiar faces here you'll get used to. Same bodies show up all the time. Okay, so we got everybody that I didn't recognize. Okay. What we're going to do tonight, we're going to start off with our speaker. And then after the speaker, we'll have a meeting. We have some business we have to conduct because it's the last meeting of the fiscal year. Next month will be our annual meeting. So we have some business to take care of tonight. So that will be done after our speaker. So at this point, I'm going to turn the meeting over to Mr. Walsh to introduce our speaker.
All right. Well, tonight we're going to hear from one of our own. Dr. Jonathan Gradie is a planetary scientist and entrepreneur. His background includes a bachelor's in astronomy and a Ph.D. in planetary sciences, both of which are from the University of Arizona. His research focus has been on applying polarization, photometric, and infrared observations to understanding the properties of asteroids, comets, and so forth. He did this work at Cornell University and then a lengthy stay at the University of Hawaii. And in fact, asteroid 3253 Gradie is named in recognition of all of that work. He currently hails from Putnam, Connecticut, very close to me. And tonight he will be talking about ground-based observations of volcanic activity on Io. So Jonathan, it's all yours.
Okay, thank you very much. I appreciate the chance to talk here. I think this is going to be a lot of fun for me since it's one of the first times, probably in decades, I've had a chance to speak on some of the fun things that go on in life. And in some sense, this is the next step in a 50-year mission that I've had, trying to understand some observations I made back in 1973. All right. Okay, we're all set. So the title of my talk is like Mysterious EO or various other things. And it really comes down to EO is a very highly studied or intensely studied subject for the last maybe 40 years. But I want to take a perspective starting about 50 years ago when I'll call it the pre-Voyager time, and see what how we can interpret the observations that were made back in 1973, and see if there's something to be done in the future. And I've started this slide off showing you Io is it appears today. By that I mean the post-Voyager period. And you can see the Jupiter-facing side, which is the tidally locked side looking into Jupiter on the left. The anti-Jupiter-facing side, that's the side we see looking out, and on, looking at it as it's crossing the face of Jupiter. And then on the right, you'll see an image with a little plume coming up, indicating that Io is a very active planet. But I want to start off first a little history. As I say, this is going to be a historical thing. It is my journey from Putnam, Connecticut in, let's say, the 1960s to Seagrave Observatory and the skyscrapers in the 2023. And I grew up in Putnam, Connecticut, 15 miles from Seagrave Observatory, but I had no idea it existed. And it's amazing that there was this nice observatory sitting not very far away, and no one who knew that I had an interest in astronomy ever mentioned it to me. And that's pre-internet. In fact, it's pre-internet. And in some sense, that experience that I've had in the pre-internet might tell us that we probably need to look at how we say advertise or relate to the general population. And I'm just saying this from someone who hasn't been in the association, that I wonder how many, even today, there are people out there who don't know Seagrave Observatory exists and could benefit from it. I had a passion for astronomy. I'm going back to see the pole print here. And I built a roll-off observatory with a 8-inch F8 Newtonian with a polar mount, Criterion Corporation, et cetera. And I'm showing this picture here. And the reason is that when I was over at the public night the other night, a couple of weeks ago, and I went into the roll-off observatory, I was just absolutely taken back to the time when I put mine together, and just being inside felt like being inside something that I had built a long time ago. The observatory is now defunct, if you will. My sister, who owns the house now, needed a storage place, and so she tore it down and rebuilt a storage shed on it. And that's okay with me, because now I find that there's some really nice telescopes 15 miles away that I can use. And you can see a picture here of me here with my 8-inch in the roll-off observatory. And in some sense, it was kind of lonely that I was the only one that used it. And well, it's a lot more fun being with people. As Ed mentioned, I went to the University of Arizona, then Cornell University, and the University of Wyoming in the planetary science research business, and then into technology transfer and small business. The idea there being that I was doing a lot of instrument development in imaging systems, spectral systems, infrared, and there were opportunities to build companies, make money. And then I retired in 2016, coming from Hawaii to Connecticut, to Woodstock, Connecticut, just down the road from Putnam. And I'll tell you, it's the nicest place to be. The only big difference is that the skies are not as dark as they used to be. But I think that there's so much to do and so many things to do. Not having dark skies isn't necessarily that important. I want to show two pictures here. The one on the right with the white telescope is the Catalina Observatory 61-inch telescope on Mount Lemmon. And I'm there with scientist, Johan Degevij, a Dutch scientist from Leiden Observatory. And he and I are putting together we're preparing a germanium bolometer for infrared observations of asteroids. That's a big, lot of words to say. But there's two things about this picture that I want to point out. The first is the telescope. It's a f13.5, 61 inch, and you go f13.5 Cassegrain. And it turns out that Gerard Kuiper had this designed specifically for planetary observations. And in fact, the same telescope was used by a fellow named R.B. Minton in 1973 when he was using a 35 millimeter camera. And think of it this way. He's sitting up on these cold nights on top of a mountain behind this telescope, staring through an eyepiece, waiting for the special instance when the seeing suddenly becomes better. This is before adaptive optics was even a dream in anybody's mind, and would snap a picture on 35 millimeter color film and just do thousands of these images and take them back to the Lunar and Planetary Lab and develop them. So that was kind of the state of the art in imaging of planetary satellites in the late 1960s and into 1970. But the infrared instrument I'm using there is one of the first ones developed by a fellow called Frank Lowe and George Ricci. Marcia Ricci, George's wife, is, I think she's chief scientist on James Webb, I think now, an infrared astronomy scientist, excellent people there. And then on the lower left is looking at the NASA IRTF at Mauna Kea over in Hawaii about 1982. And not completely in this image, but in the background, you can see these racks and racks of instruments and a paper strip chart recorder. This is 1982, and we're still using, as astronomers, some really basic technology to, or at least in our view, 50 years later, antiquated technology to discover some of the fundamental aspects of the solar system. They're quaint, as I say, compared to what we do today. Now, onto the part of the talk, which I think is going to be much more interesting, which is a historical perspective of what studies of the Galilean satellites, and particularly Io, have brought us. And you can tell by my white hair and lack of some of it that I've seen 50, almost in some sense 60 years of this study or discovery in the system, and things have changed considerably. You'd only have to go back to Galileo in 1610 to say, well, the Galilean satellites were just points of light in the sky and they just whipped around, and the only thing you could study about them was their motions, their orbits. Of course, that was fundamental and changed our understanding of, at least humans' understanding of the solar system. We fortunately start off at a little bit higher grade there when we learn what we learn in school. And it wasn't until 1927 that anybody was able to put real quantitative measures to anything in the solar system, and that was the invention of the photoelectric cell. And a guy named Stebbins started doing color measurements, and things weren't sensitive enough to be able to divide the light up into spectroscopy and do a lot of spectroscopy. So he started developing these color filters as what we now call multispectral filters. They're broadband and they're red, green, blue, ultraviolet, infrared, as best he could, but it's all dependent upon the photo response or the spectral response of the photocell. But it was clearly figured out that the reddest object in the solar system was Io, and it tended to show some color variations with orbital phase. And so it became a little bit of a mysterious object because everything else was either very dark or quite bright, such as the Saturnian satellites. Although, this is still in the 1960s and 70s, and bigger telescopes were being made, have more big telescopes, so you could collect more lights, you could make more of these measurements. And it was in 1964 that some folks at Arizona, Alan Binder and Dale Cruikshank, were observing the emergence of Io out of the eclipse of Jupiter and reported that it was brighter at eclipse than it was supposed to be. And so it indicated there might be an atmosphere on a small dead world. That's what all the Galilean satellites were looked at. And so that mystery remained, and lots of work, I mean, observations were made, but no one could make really heads or tails out of it. Pioneer 10 and 11 in 1973, in that 74, provided an accurate mass for Io. And it was very clear then that Io was very different than Europa, Ganymede, and Callisto, that Europa, Ganymede, and Callisto were water worlds, and Io wasn't. Somehow it was dry. Where did all the water go? And the unfortunate thing about that is we have a moon right next to us that's kind of like dry. And so Io began to be seen as a moon analog, and Europa, Ganymede, and Callisto garnered the more attention because there you could do models about buried oceans and things like that. And about this time, late 60s and into the 70s, these new techniques such as polarization, optical polarization of light reflected off of these planetary bodies, and infrared photometry, now not imaging, because the first infrared instruments like the one I showed you were not imaging instruments. They were little aperture instruments. There was a single detector, and you have an aperture, and you get this small aperture, put your satellite or whatever you're looking at in the center of the aperture, and the rest of the scene is excluded, and you hopefully make your measurements so there's no background contaminating the signal. And so these were kind of exciting measurements. And then again, as I said about the case of R.B. Minton, there was very careful film-based imaging that was brought to bear. And at the bottom here, I just wanted to give you an idea that, back in 1610, these were just little points of light. They weren't even sure what they were. And for most of us doing observations with backyard telescopes and when we're growing up and having fun, Jupiter and its moons are just points of light. And it turns out that for most professional astronomers doing stuff, aperture astronomy, all you do is worry about the point of light and then make up stories about what you were looking at after you get your data, kind of like the old elephant, somebody's grabbing the tail, some are grabbing the ears, and we're making up, I won't say stories, but you have to, because you have to kind of test things out. And what was happening at the time was that the suspicion was that something was going on. Io was completely dry. There was no water, but there was all this sulfur and sodium and potassium running around. So the thought was, well, maybe these are giant salt flats that Io evolved over the years. It had a lot of water, and it just all it dried up, and all it was left was were these kilometer thick, or who knows how thick, sulfates, and they would be the source of the sulfur dioxide, which was being seen spectroscopically, but no one could really figure out where was it coming from, how is it getting there, what were the energy sources. And to add mystery to it all, there are these things called sulfur allotropes that normally S8, sulfur is a chain of 8, but you can make 7, 6, 5, and whatever. And all these different allotropes of lower number of molecules have incredibly beautiful colors. They go from red, orange, yellow, green, you name it. And when you sink them down or take them down to temperatures like 130 degrees Kelvin, which is like the typical temperature in the Jovian system, they can change color even more, going from green to yellow as the absorption bands change. So everybody was saying, okay, well, we've got salt flats, we've got meteorites banging salt and sulfur and potassium out. The SO2 is coming from the decomposition of these salts. And so the post-eclipse brightening, if it really was there, could be explained away by SO2. But then some strange things happen. This is where it gets interesting for me, because this is where I started participating in this mystery. Oh, by the way, I want to point out that in the lower left, see, I have a pointer here, right? So this is what, in fact, I can, whoops, I didn't want to do that. Hang on a second, guys. Let's see if I can go back. Okay. This is what our vague image of the Galilean satellites. This is even post Pioneer 10 and 11. And Io was known to be very yellow and have what were thought to be red polar caps. And this is what R.B. Minton did. These are not actual results. These are figurative. Callisto was very dark. Europa was much brighter, and Ganymede was brighter. And already there was evidence from spectroscopy that water was on these three, but not on Io. And so the polarization measurements that we made, and this is where I'm going to talk about these a little later on, but we're going to have to go through some background before you begin to understand what I'm getting at here. That polarization talks about the disintegrated surface scattering properties. And so in the measurements were made in 1973 by myself and Dan Zellner, suggested a dynamic surface, but not post-eclipse brightening. And we presented this argument at the Bulletin of the American Association of Astronomical Association in Tucson in December 1973. And it was the first presentation I ever made. And a fellow in the audience called Gerard Kuiper got up and started asking me questions. And already, I mean, these were, scratching your head. I wonder if they're real type things, but he was extremely interested in it. And later on, of course, you figure out that already he and others were beginning to question their model of Io, but there was nothing to replace it. And at the same time, a guy named Bill Sinton at the University of Hawaii, using infrared instruments, which were being built and being tested and being put to use to try to figure out what's going on these little planetary satellites. And he found what's called an intermittent infrared brightening, and that's in the 2 to 5 micron region, indicating that there was a small source on Io radiating at about 600 degrees Kelvin. And, when you think about it, what was, everybody was like, no, that can't be. And Zellner and I were very, very tentative in saying that we had seen changes, temporal changes in the scattering properties of the surface, but we had no model to think about it. And in fact, it was a great bias. I think the whole community had this bias of trying to fit the observations that all of us were making, not just the polarization in the infrared, to the dead moon model. And I think that's a big oops, right? So in 1979, Voyager 1 flies by. Some folks, P.L. Casson et al. And Reynolds talk about tidal heating model for satellites like the Galilean satellites and resonances with themselves. All of a sudden, it was like, oh, that's what you're talking about. In other words, Voyager flies by, sees this kind of stuff, and everything else just suddenly makes sense. And then again, what happens to the polarization measurements here is they're kind of like, shall we say, forgotten, because when you take a look at this picture here and we talk about the volcanic activity on it, you'll go, oh, wait a minute, that explains it. Let's move on and do something else that's more exciting. And believe me, there are a lot of exciting things to talk about on Io, and we'll just jump into them a little bit. In particular, we want to try to understand the changes in the surface properties of Io. And this is in the type of property where the light comes down, bounces around. It's called the light scattering properties, radiative transfer properties. And they happen at the very, very top few microns or millimeters of the surface, depending on its porosity. So when we see these pictures of Io showing volcanic eruptions and turmoil and everything going on here, you say, oh, well, there's just no hope in being able to, understand the polarization stuff. Let's just go on and try to understand how the volcanoes work. Are these basaltic volcanoes or what? I want to give a little aside here that I was at Cornell University at the time, and a fellow by the name of Tommy Gold, I don't know if you have ever heard of him, but he was the fellow that explained pulsars, and he was very into electromagnetic fields and theory. And he stopped by and started telling us that his theory was that the volcanic eruptions on Io were not volcanic eruptions, the plumes, let's put that way, not volcanic eruptions. They were where the Io flux field, that is the strong magnetic field and the strong particle environment, focused down on specific spots, like these dark spots you see here, like an arc, and melted everything around and blew it off back up into space. And I hate to say it, but who knew at the time? But we just shrugged our shoulders and said, "Sure, Tommy, go off and work on your pulsars." So today we do see changes on the surface from time to time. In Galileo, well, Voyager in 1979, and then Galileo and 20 years later, and then New Horizons almost 20 years after that, 15 years after that, showing that there are changes that are occurring on Io from these volcanic eruptions. So how do we want to think about resurfacing Io? Well, okay, volcanic eruptions, that's pretty easy. But the big problem was that a typical volcanic eruption it has a source that's much greater than 600 degrees. Basaltic lavas are 1100 degrees Kelvin or 1300 degrees Kelvin. It's not, that's not right. And there were these long sinuous lava flows that seemed too fluid for basalt, but not for sulfur. Molten sulfur can flow just like water. And so there was like, oh, well, maybe this is molten sulfur because sulfur's all around, and look at those colors. But there were huge topographic differences which say sulfur doesn't support kilometer or 5 kilometer high mountains and scarps. So there's got to be a mix of something to go on. Now, to give you perspective about these plumes you see, a huge eruptive plume, that's an SO2 rich, not a water rich plume on Io. Well, if Old Faithful were placed there, it'd be 40 kilometers high. So you don't need a big source of energy, if you will, to make a big giant plume on Io. So those plumes you see might just be things like Old Faithful going off. Still, that is yet to be determined. But the key thing here is that if you're going to talk about this top layer of what you see with polarimetry or photometry, the colors, so to speak, then you got to understand what's going on underneath. And there were kind of two models that were put out. One was the interbedded sulfur and silica lavas. So you have a solid silicate underlying region with maybe a magma ocean much deeper down. This is many, many tens of kilometers down. And that what the activity we're seeing going on with the plumes going off and the calderas and stuff like that are all happening up here, and they're all done with a mixture of basalt and sulfur. Of basalt and sulfur. Another way of looking at it was that and this goes back to the idea that there are salt flats on Io. You take a model that you've been working on and you go, well, here's some new evidence. Let's see how we can adjust the model instead of maybe just throwing out the model completely. But the idea was that the solid silicates and the pools of molten silicates was all down deep, but instead you had all this molten sulfur in buried ponds and lakes and reservoirs. And on top of it was layers of sulfur dioxide with all these kinds of sulfur allotropes and who knows what on it. And so the question back just after Voyager was that, okay, you got a surface that's being resurfaced, but what is it? And of course, and this is where my colleague out in Hawaii comes into play, is that of course you go and you solve the problem by taking a field trip to Io, of course. And the fascinating thing at the time, and this is like 1984 or 85 or so, that no one had really understood what the thermal properties of a lava pond look like. We had taken data and stuff, but it tended to be Landsat type data, but the study hadn't been done. And so I happen to have this thing called a field spectrometer, which measures the intensity of light coming out of off the surface of something. And so we could use it to measure these lava ponds and looking at specific spots. Well, what was the temperature here? What was the temperature here? This on Io, by the way, would be a plume rising who knows how many kilometers up. And we began to find out that this area here, the glassy surface of the lava, basaltic lava, was like less than 600 degrees, maybe 400 degrees Kelvin, 500 degrees Kelvin. I don't want to say you could walk on it, but it was much cooler, whereas these hot spots were, again, really, really hot. And I want to point out that this is me with the field spectrometer, and this guy is a guy named Luke Flynn, and he, believe it or not, hails from Putnam, Connecticut. And he's a very well-known and productive scientist in Hawaii still, running the Space Grant Consortium and things like that. And he and I and Pete, who's on the line here, wrote a paper or two about the temperature differences and what it might mean. And so we were able to conclude that basaltic processes could explain all the observations. It wasn't sulfur exclusively. And well, so what? Oh, and this is just to remind us that when we talk about volcanic eruptions and things on Earth, we have these giant fire fountains. This is probably a kilometer high, maybe or so, of very, very hot lava coming out. And if that were to be on Io, the velocities and everything just might keep it going up, carrying the basaltic parts of it up many tens of kilometers into the air, providing a huge dust cloud or ash cloud of fine particles raining down all over the surface. And alternatively, you have images, or shall we say conceptual images, of what it might look like if a fumarole was going off, and the fumarole is just a small one of these things, maybe a meter or so in diameter. But these things go up many, many kilometers in the air. And again, raining sulfur dioxide, sulfur, basalt, silicate rocks, and everything, little tiny pieces all over the place, resurfacing the area. And so if you hear a theme about resurfacing the area, well, that's something I want you to keep in mind. So Io is the most active and bizarre satellite in the solar system. And it's been that way for over 40 years. I mean, sure, we've seen some neat things on other planets, Enceladus and its water cracks and plumes and everything is one thing, but nothing like the dominant activity that goes on Io. In fact, the resurfacing rate is thought to be about 1 millimeter per year, which means that that's a couple of inches of shall we say, covering that's been going on over the last, ever since Voyager. And so if you have this volcanism and you have this continuous eruption of stuff, and you have a resurfacing over large areas that looks like it should be happening, then the question is, are there ground-based observations that conduct these surface changes using small telescopes? And do they lend themselves to synoptic observations? And that goes back to the idea that we had seen changes in the polarization. And we'll get to that, what those changes are here in a second and what we can do about them. And then we ask the questions, well, what observational techniques are suitable for small telescopes for long period observations? And can you do it in visible light, like polarization? And we're not going to talk about this now, but I have some ideas about these things called room temperature infrared bolometers, which are used as imaging systems and staring systems. But there are many, many neat techniques that were developed back in the 60s by Frank Lowe and George Ricci to improve the detection characteristics of their initially germanium bolometers. So now we want to talk about the polarization. So let's talk about what could you do with polarization. And here's, we're going to go some definitions, and don't worry about the formulas and stuff like that. I want to build in your mind kind of like a visual sense of what might be going on. If you have a surface and you shine unpolarized light on it, then it's pretty easy from the physics to calculate the amount of polarized light and the reflected light. Now, if you take this surface, though, and you turn it into a particulate surface, a pile of fluffy sand or fluffy dust or whatever, then you'll find that the polarization of light coming off is much, much more difficult to calculate, and you're better off just observing it from an empirical way. Now, what we do in our astronomical sense is we have the sun, we have the Earth. Here we are, with our telescope here, and here's an asteroid or Io or Jupiter or something out there, and there's an angle between them. So if you're standing on the asteroid and you look at the angle between the Earth and the sun, you call that the phase angle. Now, imagine you're standing on Jupiter and you're watching the Earth go around the sun. Well, you see that phase angle. It gets big, then it gets small as it goes into inferior conjunction, and it gets big again, and then it gets small again as it goes through a conjunction. And if you watch it over enough and you start making measurements of polarization, which is just, and we've all had our polarizing sunglasses and polarizing filters, and we know we can, move them back and forth and make measurements. But if you take, perpendicular and parallel measurements, and we'll define what that is in a second, but, just rotate it 90 degrees, then you can calculate a polarization. And if you measure those polarizations as a function of the phase angle, so for us on Earth, we're watching the asteroid or the satellite or the whatever we're looking at going around the sun, okay, as it goes around the sun, the sky, we make those measurements, we get a strange curve, not so strange, but it's just what it is, goes from here from 0 to 30 degrees in that phase angle. So imagine that angle opening up. And first, the light scattering off is in the plane opposite to what's called the scattering plane. We call that the negative polarization. Just think of it as negative. And then it goes to 0 and flips around and turns 90 degrees and then continues climbing up, getting stronger and stronger as that angle gets bigger and bigger. And we define the bottom peak here as the minimum polarization, and this changing, the angle of changing called the inversion angle, where it goes from negative polarization down in here to positive polarization here. And I'm going to just, don't worry about the words so much, but this is an image now of what the scattering really looks like. It's just a bunch of little tiny particles. It's going to be ice particles, dirt particles, fine dust, big rocks, you name it. Little tiny particles coating bigger particles of all different minerals and stuff like that. So the light coming in this way gets scattered out in that way at the phase angle that you're looking at. And by using this relationship, you can probably figure out what's the scattering properties of the surface or parts of the scattering properties. And I draw your attention over to this side, just where we've plotted the minimum polarization. That's the depth of this thing here. So it gets deeper and deeper and deeper as we're going this way as a function of its albedo. And the albedo, you can think of as reflectivity for all practical purposes. It's just the reflectivity compared to a Lambertian surface, but compared to a white surface. And if you look down here, you see Ceres and Deimos and the moon, Mars, and these are pretty dark things in here. And as the surfaces get more and brighter, and up here we have Europa, here's Io, here's Rhea, Iapis. These are the the Saturnian satellites, Ganymede, Europa, and Io. Well, they have very shallow minimums and very high albedos. And when you look at Europa and Io, man, they're really reflective. So just from this, you could say, wait a minute now, if you have a surface like this, that's in time period 1, and you measure the minimum polarization and the inversion angle and stuff like that, then let's say for Io or any of these things, and you come back, next apparition, and you measure it again, and you find a slightly different set of parameters, that must mean that the surface here, the scattering properties of the surface have changed. And that's kind of what we thought might be going on Io, even before we had any idea of a volcano. And if we had mentioned fumaroles or geysers or anything like that, we would have been probably laughed off stage. And that, again, that's the bias. So this is the general result of a number of observers. This is Zellner and Gradie data in here too. So here we have that phase angle. Okay, so as Jupiter goes around the sun, it goes through opposition to elongation, back to conjunction, back to elongation, back and forth. And the satellites are going around Jupiter. We'll get to that part next. And so we were able to, go out every night, so to speak, and make a polaric measurement of Europa and Io. And you can see this is what we got for Europa. And not only that, Joe Burka, who had done some initial studies of this, and Adouin Dollfus of France, working with researchers there. He was an excellent astronomer and a colleague of Gerard Kuiper. And anyway, you see, this is the thing you get, and you're saying, oh, look, there's this P-min and whatever, we might be able to make some estimates. And you go over to Europa and you go, oh, there's a P-min. But look at the difference in inversion angles. For Europa, it's at about 6 degrees, and for Io, it's somewhere in here. Okay, and that's the first indication when you say, well, somewhere in here. And if you look at the scatter around these points here, you go, well, it doesn't really scatter very much as a function of apparition, because these are taken over a couple of decades, believe it or not. Dollfus in the 50s and early 60s, Viverka in the 60s, and Zellner and Gradie in the 70s. But if you go back to Io, and these in particular are the measurements that Zellner and I made, and I was the one that sat out of the telescope doing it every couple nights, labor of love, so to speak. It just was all over the place. In fact, the angle of polarization was changing from negative, where it should be, to suddenly positive at the same phase angle. And how can that be? Well, is it instrumental error? It could be. Is something going on? It could be. But there's an added thing in all of this stuff. And this has to do with the fact that not only are we measuring these polarization measurements as a function of phase angle, that's as Jupiter goes through its apparitions, but also in the longitude. So we're looking down on the top of Jupiter here. Thank you, Juno, for providing the imagery of the pole of Jupiter so I could put it here. And if the sun is down here and the Earth is out here, then we know this is the phase angle, okay? And so Io would have the same phase angle. But Io is tidally locked, so it always puts a face toward Jupiter. And so as it goes around, we get to see the whole longitude of Io repeat. So here from the Earth, we're looking at the leading edge. Leading in the orbit. And on this side, in the west, we're seeing it on the trailing side. We're seeing the complete opposite side. And if we're lucky enough, we can see the Jovian facing side and the anti-Jovian facing side as in the course of our observations. And so what we realized was that this whole error in here might be a combination of phase angle effects, but also rotation effects. You're looking at various faces of the thing. So we did an analysis, and I apologize in some sense, but this is really great, because this is my original plot that I made up when I took the data. And back in the day, you did a lot of things by hand. There was no Photoshop, there was no PowerPoint. There was just acetate and cut and paste, meant scissors and paste and maybe some Scotch tape. And so what I did was I plotted along here. This is the longitude of Europa, of Io as it goes around. So starting when it's on the far side of Jupiter, then to eclipsing in front of Jupiter, and then going back to its other side. And we took this to remove the phase angle out of the equation. We did this only for things that'll be around 10 and 11 degrees phase angle. And sure enough, you begin to see that there are different sides of Io. And in fact, the trailing side seems to be different than the leading side. And Voyager, indeed, at the very beginning of the picture I showed you, there are real differences between the leading and trailing side. But these are the remarkable things, and there's a couple of other observations that may not plotted on here, where the angle of the polarization changes from negative to positive at the same longitude, and at the same phase angle, same longitude, just different times. This was taken in May, and then this was taken in October. Here's another one in August, and this one is in October, I think, no, actually November. And so we're looking at this and saying, oh, wait a minute, this is weird. Why would there be these significant changes? And by the way, flipping the angle of polarization in the scattering is really difficult. So that's where things stood. We don't know the answer to it. Because there's no more data, nobody's been collecting data. Actually, I take that back. There have been people collecting data, but not in a synoptic long-term period, shall we say, mission to take lots and lots of data as frequently as possible with as high as precision as possible to see if anything happens. And to be frank, that's not the world's most exciting thing. I'd rather take a trip out to Kilauea volcano and dance with the lava, bombs coming out, than spend my days or nights at the side of a telescope. So my thought is, and this is how do I put it, for a more serious amateur that wants to do something, but the next slide will show you it's not that difficult, is that one could basically build a polarimeter to stick on a, when I say, something like a 0.2 to 0.5 meter reflecting telescope, and you can make it semi-permanently. It's just like a photometer, just a camera system. And it could be operated remotely. In other words, you put it someplace where it's clear, and then there are automatic observatories that might be game to participate in it. And you could measure the polarization and essentially anything else like near-Earth objects or asteroids or comets or something that comes in the field of view. And in my view, I could maybe reach some self-satisfaction or be chasing windmills on this thing. So building such a device isn't that hard. A guy named Tristan Wolfe at the University of Denver in 2014 put one together for an imaging system for for studying dust clouds, galactic dust clouds and things like that. And so it's pretty simple, an 8-inch Meade telescope or any telescope, off-the-shelf components that you can buy or build or manufacture. If you're, it's not that difficult. And then the big thing then becomes, well, how do you actually make the observations? Do you go out and get a automatic service to do that? And maybe you could even get money from NASA or something to do. I have no idea. And or go back to the old model of getting benefactors to fund such things, and see if this post-skyscrapers IO might be an even newer IO. Who knows what we could do? Anyway, that's my talk. If anybody has any questions, I'm free to answer. Ed, do I take my thing off here, or how do I do this? I guess,
Up
so
at
I
the-
get back,
at
I'm
the
just gonna
top.
go back here on, so I can see everybody.
Up at the
I'm
top
hoping-
of the screen, John.
Pardon? Oh,
At the
yeah,
top, you can stop sharing.
let's see, no, I want to stop sharing. Let's see. Oh, I see, here it is right here. What do? I stop share. Oh, I can
There you
move them
go.
up.
There you
There we
go.
are, okay.
You got it.
So,
I have a question.
sure, Greg.
Okay, how, as Io gets closer to Jupiter, does that affect the volcanism? Because there's more gravity as it gets closer and then further away. Does that affect the volcanic flow because of its orbit around Jupiter and the gravitational forces?
That's a very perceptive question. In fact, you're right on the fellows back in 1978, Stanton and Peel, Reynolds and Casson, Peel and Reynolds and all, that it turns out that the Galilean satellites orbiting Jupiter are in what's called a forced resonance. In other words, the satellites themselves force each other to stay in their orbits in spite of the presence of Jupiter and the oblateness of Jupiter. So what's happening to Io as it goes around Jupiter, in essence, and it's getting squished. So, Europa pulls it out, so it gets a little squished this way, and then Europa goes by and it gets squished back again, and Jupiter's, it goes up, inclination is such that it goes up and down over inclination, it's getting squish, 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 squish. That's exactly what's going on. And the amount of energy that it produces is just astounding. So if we could get some wires up there and plug it in, we could we could power all our cars forever. So that's exactly what's going on. That's where the energy is coming from, and it's not radioactive. And so I hope.
So what do you think it is, lava or sulfur?
Well, we have pretty much come to the conclusion that all the landforms you see, the morphology, the geomorphology, are determined by the basaltic silicate under basement or whatever, and that the colors that we see and much of the plumes and dynamics is this, shall we say, recycling of the volatiles, sulfur being a volatile, SO2, sulfur dioxide, and so we the kind of layered model and mixture of that is probably right. That if you take, if you look at the picture of Io and forget the colors, you go, oh, that's all basaltic volcanism. There are issues about how did the lava channels and flows flow as far as they did. And a lot of that has to do with the fact that you got a lot of power coming into that, tiny moon, and it channels itself into certain areas, and boy, they just go off. And I suspect that those flows are much hotter than flows on Earth, except for one strange difference, and that is on Earth we have water, which tends to lower the melting point of the basalts. On Io, it's completely dry. So I don't know, maybe Peter, our resident geologist from Hawaii, maybe he knows the answer to that.
Hey, no, Jonathan, it's your talk. You could mention some of the NIMS observations where they're calculating what the eruption temperatures are and the influence about energy input from individual vents.
Right. They are very, very hot. And so you can calculate, knowing the temperature, and from, if you know your physics or studied physics, and you can understand that the power radiated is proportional to the fourth power of the temperature, that the temperatures of these are very high and the power being radiated is very great. So the input power has to be very great. I don't have numbers on that, but
I actually meant that the volcano observatory that's being proposed by NASA right now.
Yeah, in fact,
It's
yeah.
built on the speculation that some of the Galileo measurements identified magma temperatures in the 14 to 1500 degrees centigrade range. That is way higher than the eruption temperature of basalts. You have to go to an even more silica poor lava, i.e. a komatiite, which is only seen on Earth very early on in Earth's history. So the magma chemistry determines what the eruption temperature is. And many of the observations that both New Horizon and the Galileo spacecraft has made are, and it's not clear whether or not you're seeing a basalt, which has about 45% silica, or a komatiite, which might be in the 35 to 38% by weight percentage. So temperatures really are very diagnostic of what the magma chemistry might be.
Thanks, Pete. By the way, Peter is a world-renowned planetary geologist, volcanologist, and he knows his stuff.
It's interesting. I love watching shadow transits of the planets on Jupiter, and I image them, and you can actually get a small disk on Io, and it's yellow with a backyard telescope nowadays with today's technology. It's amazing.
It is amazing. I saw some images taken at Pic du Midi in France using adaptive optics. And I don't know that they used, I don't think they used adaptive optics. I think they used lucky seeing. And you can actually see details, vague details on Io. But that's because of modern telescopes and just the way and the CCD cameras. That's the other thing, is that back in the day, you know, you had film. That's what I started out with, was film when I was doing my astrophotography in the 60s. And man, I'll tell you, that was really tough because you make one mistake and that ruins a lot.
Now it's changed to CMOS from CCD.
Yeah.
Any other questions, anybody?
Thank you.
I have a question. So there was an image that you shared of Io earlier, and I know that the Voyager had black and white cameras. The coloring of that photo, was that purely artistic, or was there any meaning to the colors that were chosen for that photo?
Yeah, the way those are put together is like a red, green, blue camera. So if you take a red filter, a green filter, and a blue filter, and you take essentially a black and white or monochromatic image in each one, and then you combine them together in Photoshop, if you will, you say, well, the red intensity is here, the blue intensity is there, and the green intensity is there. That color that we perceive in our eye, and that's how they produce those color images. But what added to that is that since these cameras can use filters that our eyes can't see at, like near infrared or in the ultraviolet or narrow band, so they can slice it up and produce a color image, a pseudo color image, then yeah, you can get bizarrely enhanced images that if you were to go there in person and take a look, I wouldn't say it wouldn't anything like it, but it would look different. So the important thing, though, about those color images is that the color is not put there for an artistic purpose. It's looked there to translate that information into something that humans can understand. That green's different than red is different than blue. And that's what that's about. Does that help?
Yeah, thank you.
Anybody else?
Yeah, I promised to give him a hard time. Can I ask?
Oh, have at it. Have at it.
Jonathan, I'd be interested to hear your point of view. What's the point of looking at time-varying polarization signatures? What would you hope to interpret about the surface of Io if you saw at any given longitude on Io, you had time variations in the polarimetry. Apart from
That's
proving you were right in 73.
Okay, that's an excellent, that's actually an excellent image. Its real impetus is that that if you can detect these changes as a function of time, then the surface property is changing as a function of time, and that's changing as a function of the eruptions going off. Whereas the infrared observations tell you about the eruption site, if you will, the temperature of the eruption site, the polarization measurements tell you the broad extent, if you will, of where the plume went or where it's going. Now that's a speculation, so I don't want to push it at that, but that's what you'd want to do, because then you could have a monitoring device that tells you, independent of an infrared system, which can be, I think, very expensive, although I think I'd like to find out a cheaper way to do that, that then you could monitor Io and see the extent of the surface changes by aerial extent. That means that if you've got a big change in polarization, you've changed a big area.
So what you didn't say was the spatial resolution you'd expect.
Oh, you don't need any spatial resolution.
So how?
You mean if okay, that's a little complicated, and because it's a combination of whatever material is falling out of the sky resurfacing, has a, shall we say, a certain power to it to change the polarization, and the bigger an extent it is, the bigger power it has. But how do you divide out material one, which has low power over a large area? When I say power, I'm talking polarization power, not energy, versus a material that rains out over a small area but has the equivalent effect on the disk. So it's tough.
Yeah, been there.
Okay, seems like we're done, Ed.
Well, Jonathan, thank you so much. This was great.